Okay, so dear MA3293 students, this is the third lecture in chapter 4, and I'm recording this as a video lecture. In the past two lectures, we covered the following material. In the first lecture, what did we do? We explained what is the basic concept of a shock, and we showed the mechanical origins of what a shock is. So essentially what we showed is a shock is a bunch of acoustic waves, or what is called as infinitesimally weak signal propagation mechanisms, which are essentially pressure waves merging together. Okay, and these infinitesimally weak pressure waves, or so-called acoustic waves, can merge together only in the case of what is called as a compression shock. That is, the effect of the shock is going to leave the gas behind the shock compressed. Okay. In the case of an expansion shock, we observed that these acoustic waves or information propagation waves don't coalesce into each other. They spread apart from each other. And mechanistically, we showed that this is the reason why expansion shocks in a generic situation is not feasible. Of course, there are some extreme cases, or what is called as outlier situations, where expansion shocks, and that too weak expansion shocks, can form, but that's beyond the scope of this course. In the second lecture for this chapter, we derived the basic equations for flow across a shock. So what did we do? We assumed a plane normal shock that is stationary and the flow is 1D, which means it's uniform flow in the direction transverse to that one-dimensional flow direction. And what did we do? We first derived using a simple control volume analysis. So we drew a simple control volume around the shock. So imagine I have a shock like this. Okay, so I have a shock like this. What I did was I just drew a thin control volume. The shock is a very thin layer, so it has infinitesimal thickness. So this is kind of epsilon, where epsilon tends to 0, and it's basically 1D flow. Because it's thin, the area in the front and behind the shock for this control volume are not that different. So because epsilon, in other words, we can state this as epsilon, if you call this as A plus dA, then as epsilon tends to 0, dA tends to 0. So that's kind of what we did. And so it became a rectangular control volume instead of a trapezoidal control volume that we used in the previous chapter for isentropic flow. And what did we observe? We derived the reduced forms of the conservation equations for mass, momentum, energy, and the reduced forms turned out to be what we call as the jump conditions for across the shock. So what these jump conditions do is they allow you to relate the state of the flow in front of the shock and behind the shock. And the convention here is if the flow is going from left to right, the front of the shock is essentially the region of the flow before the shock, and the behind the shock essentially means the region after the shock. Okay, in the direction of the flow. So that's the convention, that's the interpretation. And what did we do? So we derived these, so we took this, then we derived jump conditions, okay, and then as we derived jump conditions, we took the energy jump condition and simplified it. That is, we wrote it in terms, we assumed it's a perfect gas, so on and so forth. So we derived equations for temperature change across the shock, which is equation 91 here. Okay, so that is then we derived equation 91, which is this guy, and then we use the momentum balance. We derived equation 93, which is here. Okay, and let me kind of put this somewhere here. Okay, and what else? Now we assumed equation of state which is an ideal gas equation of state, and that gave me equation 94. Okay, and that gave me equation 94. Now, so the one thing that we didn't use so far in deriving these equations is the mass conservation across the shock, or what is called as the jump condition derived from the mass conservation across the shock. So you take all of this, then you add this to rho 1 v1 equals rho 2 v2, which is the mass conservation across the shock, and you simplify it, you get, this gives you equation 101. Okay, so this is an interesting equation. So now this interesting equation 101 is that it can relate, if you know M1 and if you know what the gas is, and which means you know what gamma for the gas is, you can get M2, right? So what this means is, if you know the inflow Mach number and you know there's going to be a shock, then if you know the Mach number at the location before the shock, you can get the Mach number behind at the location immediately after the shock. Which in the spatial coordinate system, since the shock is infinitesimally thin, it will be the same location. So, which means from a continuous function perspective, if the Mach number is not going to be a continuous function, right? Because at the same location, so which means at, say, the location of the shock is x equals a, then x equals a plus is going to give you a Mach number value of m1, and x equals a minus, let me rephrase. So x equals a plus is going to give you m2, and x equals a minus is going to give you m1, the Mach number behind the shock, which means as you go from a minus to a plus, the Mach number is going to drop across the shock. Okay, so these expressions are quite powerful in that sense, that if I know m1 using equation 101, I can get m2, and once I know m2, I can plug m1 and m2 here, that is equation 91 to 93. So I can plug these equations here. Okay, so let me put this arrow this way. So once I know this, I can plug this equation here, and I can get P1 by P2, T1 by T2, rho 1 by rho 2, all of them. Okay, and which means I can get the jump in the property, the ratio of the jumps in the property across the shock. Okay, so now we use these equations, we derive them obviously. So from a problem solving standpoint, this helps us. But what is the interpretation, right? So we had some fantastic interpretations that we made last class. The first one is obviously your M1 needs to be supersonic and M2 needs to be subsonic for a shock to exist, because the shock is a compression shock, and that is the mechanistic reason. The mathematical reason, or the thermodynamic reason, is that we computed, using all of these expressions, we computed S2 minus S1, and we observed that S2 minus S1 is greater than or equal to 0, that is, it satisfies second law only if this S2 minus S1 is greater than 0 only when M2 less than M1. Okay, so this is the condition. And the other thing that we observed is, for this equation, we observed the following, right? If M1 greater than 1, M2 less than 1, and if M2 greater than 1, M1 tends to be less than 1. So they used to kind of assume pairs of solutions, right? So the same pair of solution will work for both M1 and M2 if you switch them over, okay? For example, if M1 is 2 and M2 is 0.5, then M1 equals 0.5 will give you M2 equals 2, okay? And what we observed is, from second law, this guy is not possible, okay? So which means M1 greater than 1 which means the incoming flow needs to be supersonic, and M2 less than 1, the outgoing flow behind the shock needs to be subsonic. So that's the only solution possible. And when does this happen? This happens if you take this to this equation, that is my P1 by P2 is 1 plus gamma M2 squared by 1 plus gamma M1 squared, right? So my M2 is basically less than 1. This is greater than 1, which means my P1 by P2 is, this entire function is less than 1. Which means if my entire function is less than 1, my P2 is higher, or the flow is getting compressed. So this implies compression. Okay, so this is the basic idea. So we derived these equations, and we learned quite a bit about the physics. So and we say we observed that only a compression shock is possible. Okay, so now it is high time that we actually relate this particular material to what we learned in the previous lecture. Okay, I'm sorry, in the previous chapter. In chapter 3, what did we focus on? We focused on primarily isentropic flow, right? What did we do? So we focused on isentropic flow in a nozzle, okay? And what did we say there? So we discussed a lot of physics there, but one of the major things that we took away from the chapter is so this is X, then your P, T, M, A are all functions of X. And P naught, T naught, rho naught are invariants, which implies that if I know P naught comma P at say x1, then I can get M of x1, okay? And if I know T naught, okay, so to this, if I add T naught, I can get T of x1, which means I can get rho naught comma rho of x1. So which means if I know P naught and the pressure at any location, I can get the Mach number, and if I also know T naught, I can get the temperature. I can pretty much get everything that I want at that location. Or the other way of saying it is, if I know P naught and T naught, and if I have the Mach number, I can pretty much get all the properties that I need, right? So this is true. And this is true for isentropic flow. Okay? So in the previous chapter, in chapter 3, this is what we did in chapter 3, right? In chapter 3, we were learning how to compute the pressure, temperature, rho, the static properties at a location if we know the stagnation properties. Right? And we also learned that the stagnation properties are invariant. In this chapter, so far what we are focused on is just the region around the shock. Okay? So we are not considering the entire nozzle. We will consider the entire nozzle soon enough, but we haven't considered the entire nozzle so far in chapter 4. We just focused on just this narrow region around the shock. And what we have derived so far is just the equation that relates the property in front of the shock to the properties behind the shock. Okay? And so that is, and the other thing that we learned is the shock is a non-isentropic process. Okay? It's not an isentropic flow. It's a non-isentropic flow. So we are focused on just deriving the equations for the non-isentropic part of the flow. And what else did we say? We also assumed that the shock is only non-isentropic, but before the shock and after the shock, the flow. For example, if I have a shock here, so if I have a shock here in the nozzle, then this is isentropic. Okay, let me write it. Okay, so this is isentropic. This is isentropic. This region is not isentropic. Okay, so we have only so in this chapter we have derived equations for the physics that is non-isentropic, and in the previous chapters we have derived equations for the physics that is isentropic. Okay, so pretty soon, in probably the next few minutes even, we will learn how to combine these. Okay, but before that, I want to look at you guys to look at these set of four equations. So let me zoom it out a little bit. Okay, so we have these set of four equations, right? 91, 93, 94, 91, 93, 94, and 101. So these four equations look at the structure. The left-hand side is the ratio, T1 by T2, P1 by P2, rho 1 by rho 2 in these first three equations. The right-hand side, if you know gamma, requires M1 and M2. And the fourth equation is M2 as a function of gamma and M1. So which means if I can plug in this expression for M2 squared, okay, if I can plug this M2 squared expression here, okay, then each of these equations, T1 by T2, rho 1 by rho 2, and P1 by P2 can be written purely as a function of M1. Okay, so which means now I can get three equations that essentially relate T1 by T2 as a function of Mach number M1, P1 by P2 as a function of Mach number M1, and rho 1 by rho 2 as a function of Mach number M1, and M2 is already a function of Mach number M1. Which means if I know M1 and if I know a shock exists, then I can pretty much get everything that I need to know about the ratio of property jumps across the shock, which means I can get the Mach number behind the shock using equation 101, and then I can, once I know M2, I can plug it in 91, 93, and 94 to get the ratios. So now we're going to derive a new set of equations. So here what I'm showing is I'm writing T2 by T1 is 1 plus gamma minus 1 by 2 M1 squared by 1 plus gamma minus 1 by 2 M2 squared, right? So use equation 101 for this M2 squared, which is this guy, okay? So let me kind of block this material here. Okay, sorry for the messy writing. So now I'm going to plug this equation 101 that we derived here, so which is this equation. So this is the equation 101, okay? This is the equation 101. We use that equation 101 to, let's see, okay, where did I go? I'm sorry. So I have this equation 101, plug this in here, and then I'm going to have a slightly messy expression which I can simplify, okay, which I can simplify here, and I get a nice final expression where T2 by T1 is basically, this guy is purely a function of M1. So my T2 by T1 equals a function of M1. Okay, similarly I can derive P2 by P1, which is a function of, so this is, let's call this as G of M1. In principle it should be G of gamma comma M1, but I'm assuming gamma is a constant that typically does not vary that much. So let's assume gamma is some constant, right? So G is a function, so this P2 by P1 is again going to be dependent only on the function, on the value of Mach number of the incoming flow, which is M1. Okay, and if you know P2 by P1 and T2 by T1, I can get using ideal gas equation of state, which means using 102 and 103, we get rho 1 by rho 2, right? Okay, so we can do that, and that's pretty much what it is. Those are your textbook mentions a little subtle observation, which I think is in some ways useful. What the textbook says is if you use the mass conservation jump condition, okay, then you get rho 1 v1 equals rho 2 v2. So instead of using this approach, it uses this equation, and your rho 1 by rho 2 is nothing but v2 by v1. Okay, this is a useful relationship. This is a useful relationship. And it's writing this v2 as a function of Mach number times speed of sound. So it's m2 times a2 divided by this. So this is m2 a2, and this is m1 a1. So now I have this v2. And what is my a2? Since the flow is isentropic in front of the shock and behind the shock, I can write my a2 as square root of gamma r t2, so the square, and my a1 as square root of gamma r t1, which means I can cancel the gamma and R terms, so I'm getting M2 by M1 times square root of T2 by T1, and I already know the expression for T2 by T1, and I already know the expression for M2, so which means I can simplify. So it's amazing. I have skipped the steps here, but it's easy to derive. So my rho 2 by rho 1 equals V1 by V2 equals gamma plus 1 M1 squared by gamma minus 1 M1 squared plus 2. Okay, so this is quite interesting. So if you know rho 2 by rho 1 using the mass conservation, I can also get V1 by V2. Okay, so this is an interesting part of the notes that I want to highlight. Okay, so which means I've numbered these new set of equations as 104 for rho 2 by rho 1, 103 for P2 by P1, and 102 for T2 by T1. That is, these new equations where T2 by T1, P2 by P1, rho 2 by rho 1 are written purely as a function of Mach number M1 alone. Okay, and this is the statement that is worth highlighting, which means if I know these equations, 101 to 104, then if I know M1 from these equations, I can get M2, which is equation 101, P2 by P1, okay, which I think is equation, let me see, which is equation 103. So this is 101, 103, 102, and this both of them is 104. Okay, so using these equations, I can pretty much get P2 by P1, T2 by T1, and rho 2 by rho 1. Okay, so that is where we stand. Right now, I know if I know what M1 is at a given location, right, and I know that a shock is going to happen at that location in the nozzle, then I know immediately using these expressions. Okay, imagine I have a nozzle and I have a shock at some location in the diverging section of the nozzle, say at a location where my area is 2 times the throat area, okay, in the diverging section of the nozzle. Then if I know P naught and if I know that the flow is choked, then my A star is going to be A throat, so my AE by AT, my A location of interest is 2 times the throat area, so which means my A by A star at the location of interest is 2, right? So if I know the A by A star at the location of interest, and if I know gamma, I can use isentropic flow, right? That isentropic flow is valid in front of the shock. And if I know I'm going to have a shock at A by A star equals 2, say hypothetically, that's what the problem says. Then I can look into my tables for A by A star, compute the Mach number at that location. So that would be the isentropic flow Mach number at that location, and that would be the Mach number just in front of the shock. So that would be my M1. And if I know my M1, I can plug into these equations, okay? I can plug into these equations, so let me use a different color just to highlight, okay? So I can plug into these equations and get my P2 by M2, P2 by P1, T2 by T1, rho 2 by rho 1, etc. Okay, right? Okay, that's how you do use that information. And obviously, once I know M2, my M2 is the new Mach number at that location. But this M2 is a new Mach number for the flow behind the shock. Now, the flow behind the shock is again isentropic, and I know, okay, I know at that location. At the location where my area is 2 times the throat area, which is, let's call that location, that area of cross section as AS, right? A shock. So at the location where A shock, the M2 for the second isentropic flow, my M2 is, say, now some value, okay, that is computed from these shock relationships, okay? And once I know the shock relationships, now I know M2. And I obviously need to know, now if I want to compute the P2, I know what my P2 by P1 is, okay? So if I want to know what are the other properties, I know the Mach number at this new location, at this for the second isentropic flow, and which means if I know P naught for the second isentropic flow, And remember, these P naught, T naughts are invariants for the isentropic flow, okay? So if you know the P naught for the second isentropic flow, then I can get P2, and then I can get T2, so on and so forth. So now we are going to combine what we have learned through this example problem, and what the equations that we have derived for the shock with the equations that we derived in the previous chapter, in chapter 3 for isentropic flow. And then after we combine these two, we'll be able to solve for flow through a nozzle with a shock. Okay, and let me go over and help you derive those. Okay, so in in the nozzle, so let me draw a schematic. So I'm sorry that the size of the document is kind of going to prevent me from making this into a nice big picture, but let's imagine. Okay, let me actually, what I can do is I'm going to insert a new page. Okay, insert a new page here. So okay, so now consider a nozzle like this. Consider a nozzle. Okay. Now somehow a shock forms at this location. Okay, it's a normal shock. Okay, and what else? So here the property at this location, so let me draw a small hash line to represent the location in front of the shock and a small location behind the shock. Okay, and these are separated by an epsilon, and epsilon is very small. Say epsilon is about 10 power minus 7, okay, or something like that. It's a micron, okay, about order of a micron. Okay, so this is epsilon is 10 power minus 7. Then I'm going to have P1, T1, rho 1, M1. Okay, let's call this and this, both these as AS, which is the shock area. Okay, and then behind the shock I'm going to have P2, T2, rho 2, M2. Okay, and let's call this, so this is going to be isentropic flow 1. Okay, and this is isentropic flow 2. Okay, so which means, what did we learn from chapter 3? Each isentropic flow in a 1D steady nozzle flow is characterized by a unique value of P naught and T naught, right? So let's call this guy, okay, let me use, which means there is a unique P naught, comma 1, T naught, comma 1 corresponding to isentropic flow 1, okay, and rho naught, comma 1, okay. Similarly, there is a unique, okay, P naught 2, T naught 2, rho naught 2. Okay, so I guess I did not put a comma on the other side, so I'm just going to make it as P naught 1, okay, rho naught 1. Okay, now let me kind of draw this guy. So let's circle this and this. Now the question is, let me use a blue color. How are these related to each other? Okay, and that is the question we are trying to answer. Okay, answer C, next page. Okay, so that's what we are trying to do. So so what we can do is, for this isentropic flow region 2, you can use the isentropic flow relationships, which is T02 by T2 equals 1 plus gamma minus 1 by 2 M2 squared, right? So this is, let me use a different color, okay, behind the shock, at AS behind the shock. Okay, and this is valid at AS in front of the shock. So you can call this at AS plus, that is just behind the shock, at AS minus in front of the shock. Okay, at AS minus in front of the shock. Similarly, this is at AS plus, at AS minus. So let me go to the previous image. Let me kind of characterize this. So this is AS minus and this is AS plus, okay? AS equals AS minus equals AS plus. Okay, clear? Okay, so mathematically we have cleared it, right? So now these expressions are valid because the flow is isentropic just in front of the shock and just behind the shock. The only place where the isentropic relations are not valid is for the region across the shock. But for those reasons, we have already computed what P2 by P1 is and what T2 by T1 is, right? As a function of M1. So you can similarly, this is again this is valid at AS plus, at AS minus. So now you can combine these chapter 3 expressions, right? These isentropic flow expressions with the expressions that you already derived for the jump in properties across the shock, right? The T2 by T1 expressions, the P2 by P1 expressions that you derived in chapter 4. And that's what we are doing here. So what we are saying is we need to compute this guy. So what is this guy? To compute this. Okay, to compute this, we write it as T02 by T2. So this is isentropic 2. This is isentropic 1. This is shock jump. Okay, this is isentropic 2 equation, isentropic 1 equation, and this is the shock jump equation. So you can write each of these guys as a function of M2 squared, M1 squared. So T02 by T2 is 1 plus gamma minus 1 by 2 M2 squared. Okay, and T01 by T1 is 1 plus gamma minus, let's see, 1 plus gamma minus 1 by 2 M1 squared, and T2 by T1, so this is your equation 102. Okay, so equation 102 that you derived for T2 by T1, which is a shock jump condition. So you plug them all in this place and you can simplify this. So the 1 plus gamma minus 1 by 2 M1 squared gets cancelled out, and these other terms you can simplify, and you would observe, so you have to plug in the expression for M2 squared. Okay, so for this guy you have to plug this in. Okay, you have to plug this expression from, which is equation 101. Okay, you plug this in this expression, you simplify it. Okay, you do a whole bunch of simplification here. I don't want to go through the steps obviously, and you would observe that T02 by T01 is 1, which means your T02 equals T01, or the most important takeaway message is the stagnation temperature across a stationary adiabatic normal shock is invariant. Okay, so let me see, there's some text material here that I don't want to miss. Okay, and this is not surprising. Okay, this is not a surprising result at all, and there's a reason why it is not surprising. Okay, and there's a reason why it is not surprising. This is because the control volume analysis for the energy across the shock gives you a jump condition, right? And what is that jump condition? Which is the equation 90, h1 plus v1 squared by 2 equals h2 plus v2 squared by 2, correct? And this is the equation. I'm sorry, this is the equation, okay? So if so this is that equation, okay? So, and what we observe, let me put this here, okay? So, and what we observe is your h1 plus v1 squared by 2 is nothing but what? It's h naught, but h naught corresponding to, what is this guy, right? We can write this. So this is h naught at AS minus, and this guy is h naught at AS plus, okay? And what does this equation tell you? That the h naught at AS minus is the same as h naught at AS plus, okay? And what do we know already? That the h naught remains invariant, right, for the isentropic flow. So h naught at AS minus is the h naught in isentropic flow 1, and h naught at AS plus is corresponds to, this is isentropic flow 2, this is isent 1, okay? And this tells you that my h naught does not change across the shock. That's the jump condition. And for a perfect gas where Cp is a constant, you can write h naught as Cp times T naught 2 for h naught 2 or h naught at AS plus, right? And you can write h naught 1 or h naught at AS minus as Cp times T naught 1, which means my T naught 2 equals T naught 1 because the Cp is constant. So that's kind of the simple derivation for this flow. Similarly, I can compute, I know the expression for P naught 2 by P naught by P2. This is isentropic flow 2, this is isent 1, okay, and this is shock equation. So I can combine these three equations. So I can get P naught 2 by P naught 1 is P naught 2 by P2 times P2 by P1 times P naught 1 by P naught 1, P1 by P naught 1. So I can simplify this expression and I can plug in wherever I have M2 squared using this expression, okay? So wherever I have M2 squared in any terms where I can plug this in. So after much simplification, so I have put a dot 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 here, okay? I'm not interested in simplifying it. You get this expression. So my P naught 2 by P naught 1 is gamma plus 1 by 2 M1 squared by 1 plus gamma minus 1 by 2 M1 squared raised to gamma by gamma minus 1 times 1 divided by 2 gamma by gamma plus 1 M1 squared minus gamma minus 1 by gamma plus 1. This entire term raised to 1 by gamma minus 1, okay? So so this term is a complicated expression, okay? This is this corresponds to equation, let me see what the equation number in the textbook is, equation 415 in your textbook and 111 in our notes. So this equation relates P naught 2 by P naught 1, the stagnation pressure on either side of the shock, or the stagnation pressure corresponding to the two isentropic flows on either side of the shock, to the inflow Mach number, M1, okay? So this is quite interesting. So let me ask you, right? We already know that P2 by P1 is going to be greater than 1, right? Because it's a compression shock. If my M1 is supersonic, M2 is subsonic, which means my supersonic flow, my P2 by P1 is greater than 1. So we know that, correct? Or my P1 by P2 is less than 1. But now it's interesting, okay? Now it's interesting. My P naught itself is changing, okay? My P naught itself is changing, okay? So this whole idea of us saying that, so the Mach number, okay, is a measure of the relative distribution of kinetic energy in the flow to the latent potential energy in the flow, okay? But this interpretation is correct, but it needs to be kept interpreted in the context of the energy remaining the same. So if my M1 is 2 and M1 and M2 is 0.5, then it's the same energy in the flow, and my energy is conserved. Okay, so which means my total energy is conserved. So this interpretation is correct. But we also have to understand that my stagnation pressure P naught is not remaining the same. So what happens to P naught 2 by P naught 1? If you do mathematical analysis, you can analyze this equation to see what it is, but P naught 2 by P naught 1 will end up being smaller than 1. Okay? Okay? So this will be 1 plus gamma minus 1 by 2 m2 squared by 1 plus gamma m2 squared. Okay? So this is actually this is incorrect way of deriving it. Okay, so this is not, so I'm going to erase this material. This is not true. Okay, right. Okay, what is my P naught 2 by P naught 1 expression? This is 1 plus, yeah, so it's 1 plus. So this is true. Okay, so this is the expression. So this is P naught 2 by P naught 1 equals 1 plus gamma minus 1 by 2 m2 squared divided by 1 plus gamma m2 squared, or 1 plus gamma minus 1 by 2 m2 squared raised to gamma by gamma minus 1 by 1 plus gamma m2 squared should be less than 1, the corresponding expression for m1 squared. So this is 1 plus gamma minus 1 by 2 m1 squared raised to gamma by gamma minus 1 divided by 1 plus gamma m1 squared. Okay, so this is the expression. So this is true. Okay, and you want to prove that this is true, be my guest. But the easiest way to prove is to put values for to see this is, and okay, let me see, this entire thing is an increasing function of m. Okay, so this is an increasing function of m, so which means if my m2 is smaller than m1, which means so this left hand side is going to be smaller than the right hand side, or the ratio of this is going to be less than 1. So my P naught 2 is going to decrease across the shock. And what is the other interpretation? Why does P naught decrease across the shock? My energy doesn't change across the shock, but P naught is the inherent stagnation pressure, and that my stagnation pressure itself changes across the shock. And the reason why it changes across the shock is the following. So you can consider this equation for entropy, okay, which is something that we derived, right? And this entropy is a state equation. Okay, so this is the equation across the state. Okay, and so you can and it's path independent. So in principle, you can, this equation is valid as you go from, say, path 1 as from state 1 to state 2. Okay, so 1 is the state in front of the shock and 2 is the state behind the shock. Okay, and using 105 and 106, you can use isentropic flow relationships on either side. So you can write this. So you can use T naught 2 by T2 is 1 plus gamma minus 1 by 2 m2 squared. T naught 1 by T1 is 1 plus gamma minus 1 by 2 m1 squared. Okay, you can similarly use the expression for P naught 2 by P2 and P naught 1 by P1 on either side of the shock. These are isentropic flow expressions, and the flow is isentropic on either side of the shock. So you can use them without feeling guilty. Okay, so you substitute what I'm doing here is I'm creating expressions for T2 by T1 and P2 by P1 in terms of T naught 1 and T naught 2 and P naught 1 and P naught 2, and that's what I'm doing. Okay, so I'm writing T2 by T1. So this is my T2 by T1 term, and this is my P2 by P1 term. So as I do this, okay, as I do this, my these terms, so my T02 and T01 are the same, right? We have already proven that. So I'm going to cancel them, and this is the expression for P02 and P01. The Cp, I'm writing it as gamma r by gamma minus 1, which means I can bring this gamma by gamma minus 1 into the logarithm, so it's going to be 1 plus gamma minus 1 by 2 m1 squared raised to gamma by gamma minus 1, right? So which means as I do this, okay, my expression is going to be okay, so I can bring this as gamma by gamma minus 1, so that is this term, this first term. The second term I can write, so this is log of some term P02 by P01 times this other term, right? So I can split this as log of AB as log of A plus log of B, right? So I'm writing this as r log P02 by P01 minus r log this other term. And this other term happens to be the same as this first term, so I can cancel both of them. And so my S2 minus S1 is minus r log P02 by P01, or the other way of writing this is my P02 by P01 is E power minus S2 minus S1 by R, okay? For second law of thermodynamics, for an adiabatic process, what should be your S2 minus S1 or delta S? It should be greater than 0, correct? So which means my S2 minus S1 should be greater than 0, or this exponent in this expression here is going to be negative, right? My S2 minus S1 is greater than 0, then minus S2 minus S1 by R is going to be a negative number. So E power minus negative number means P02 by P01 is less than 1, or my P02 is decreasing, okay? So that is how this guy, the stagnation pressure decreases across the shock. Okay, so this is a very powerful and interesting fact to keep in mind. So this is a very important expression. Okay, so I'm going to put, okay, so which means if you know the temperature jumps across the shock, and if you know the pressure jumps across the shock, or you know the ratio, that is P2 by P1, T2 by T1, you can compute S2 minus S1, which means using the computation for S2 minus S1, you can compute what is the loss of stagnation pressure across the shock. So across the shock, the stagnation pressure is going to decrease. Now you can, using this expression, quantify it. And if my P02 by P01 is 0.5, then I'm losing about 50% of the stagnation pressure. And this is a very critical parameter when you're designing nozzles, okay? You don't want to lose the stagnation pressure because it's very difficult to build stagnation pressure, okay? You don't want to lose the stagnation pressure just like that, okay? That is the first thing that I want to talk about. Let's see, okay? That is the first thing. So now, you have we have derived a whole bunch of functions, right? So all the functions we have derived, that is T2 by T1 as a function of Mach number, P2 by P1 is a function of Mach number, ρ2 by ρ1 is a function of Mach number, which is equations 101, 102, 103, and 104. 101 is the equation for M2 as a function of Mach number. Now, in addition, you have another function, which is P02 by P01, also derived as a function of Mach number, which is equation 111, okay? So now you not only have the ratio of the static properties across the shock as a function of Mach number, you also have the stagnation properties across the shock as a function of Mach number, okay? Oh, and by the way, okay, T02 by T01 is 1, okay? It's not even a function of Mach number. Okay, so that is already there, and if you want to really include it here, let's find the equation number. What is it? 28. So let's see, what is that equation? 107, right? Okay, so that is 107 equation. So that is equation 107. Okay, so you have all these equations, which means if I know P02 by P01 and T02 by T01, in principle I can derive ρ02 by ρ01, right? And what is ρ02? Okay, what is ρ02 by ρ01? So this will be, okay, let me see, right? So you can derive it really. So this will be the same as ρ02 by ρ01 as well, okay? Okay, this will be the same as rho naught 2 by rho naught 1. So let's kind of take a moment to review all the equations that we have derived in chapter 4. So we started off with the jump conditions, then we derived T2 by T1 as a function of M1 and M2, and then we finally derived an equation for M2 in terms of M1, which means now we derived new equations that can relate T2 by T1 purely to the inflow Mach number M1, and then we combine these with the corresponding equation for isentropic flow on either side of the shock, and now we have equations for T02 by T01, that is the change in stagnation pressure and stagnation temperature across the shock. For the stagnation temperature, the ratio is 1. For the stagnation pressure, the ratio is a function of Mach number, which is less than 1. Okay. So obviously, if you look at this equation, right, this system of equations, we derive T2 by T1 as a function of Mach number, my P2 by P1 as another function of Mach number, my rho 2 by rho 1 as another function of Mach number, right? So which means in principle, okay, in principle, we can have T2 by T1 equals a function alpha of P2 by P1, and P2 by P1 equals another function beta of rho 2 by rho 1, correct? Okay, that is what we are doing next. So let me spend another 5 more minutes. So we derive what is called as the Rankine-Hugoniot relationships. Okay, and these relationships are basically what we are trying to do is the same, the thing that I just mentioned. So we are trying to relate P2 by P1 to rho 2 by rho 1. These are useful relationships. Okay, I mean it's not like you have to remember you need all these equations in every scenario, but sometimes if you know P2 by P1, if you directly want rho 2 by rho 1 or vice versa, it's easy to use these relationships. So hence, and there was some other historical significance for this relationship, because there's something called as a Rankine, there's something called as a Riemann problem, which is related to the Rankine-Hugoniot relationship, okay? So I'm not going to get into that, but, and obviously it's easy to derive, the derivation steps are here. So essentially it's using the mass jump condition and the momentum jump condition, which is pretty much the beginning point or the starting point for each of these equations that we have derived so far, okay? And using that, you have to do a whole bunch of, plug and play and rearrangement of the terms, and ultimately you get this really nice equation. So let me circle this. So you get these P2 by P1 as a function of rho 2 by rho 1, or rho 2 by rho 1 as a function of P2 by P1, which is an interesting relationship, which means without the knowledge of the inflow Mach number M1 and the sound speed, etc., just by knowing P2 by P1 or rho 2 by rho 1 gives you the jump properties across the shock, right? Because if you know P2 by P1, rho 2 by rho 1, you can get T2 by T1 for a perfect gas, or if you know the equation of state, okay? So this is a very interesting observation. Okay, there's also another relationship which is called as a Prandtl's relationship for normal shock waves. It's again, these are all derivative relationships. Okay, and the Prandtl relationship is again, the origin is the jump conditions. Okay, and you start with the jump conditions, and then you kind of play around and do a whole bunch of substitutions. I'm not going to derive these for you guys, you can read it, but what this tells you is this Prandtl's equation for normal shocks. Okay, let me, for normal shocks, right? So this is called as the Prandtl's equation for normal shocks. Let's see, I have to, okay. And this Prandtl's equation essentially relates V1, V2 to A0 squared, okay, where A0 is the stagnation speed of sound, right? What is the stagnation speed of sound? This is nothing but gamma or T0. So a speed of sound based on the stagnation temperature, okay? That is, if the gas is stationary, then what is the speed of sound, okay? And so it tells you that the product of the velocity behind the shock and in front of the shock is related to the stagnation speed of sound, and it's a constant, okay? So so the question is, Okay, let me just look into this a little bit. Okay, so this is, yes, so this is gamma. So the question is this T naught 1 or T naught 2, right? So that's the question. The answer is it does not matter, as T naught 1, T naught 2 equals T naught 1, okay? So this is that T naught. So this is, the T naught doesn't change across the shocks, which means you can have a fixed T naught, and it's the speed of sound corresponding to the T naught. So this V1, V2 is a constant, okay? So which means for a given flow, T naught, V1, V2 equals constant. Okay, so it's interesting relationship. Again, you know, you have to, these are not commonly used expressions, but sometimes, for depending on the application problem of interest, you could potentially do this. Okay, so let me take a break here, and then in tomorrow's class or the next class, I'll focus on characterizing the strength of the normal shock. Okay, thank you.